Hello and welcome to our last Zoom session units on 110 acoustics and psychoacoustics. We are looking today at non-electronic acoustic modifications, Unit 7. Not sure if we'll get it done today, but I think, well, we'll see what happens. This unit is very different from all other previous units of the course because it's directly related, of course, to the hearing aids themselves. Non-electronic acoustic modifications. Long word and bunch of syllables. Let's take a peek at what we've got here. So I will share screen and we'll move to see what some of this stuff is. Okay, shrink that guy, enlarge this. Here we go. Here would be our Word document on it, non-electronic acoustic modifications. And it basically, I believe, is a two-page thing. Okay, I'm scrolling down to the very end. Yeah, it's a two-page Microsoft Word document here, and it covers three general areas. I'm just going to highlight this right away. Three areas in the middle of page one. You'll see venting, you'll see damping and filtering, and horns. Those are the three elements that we will be talking about today. And the biggest of these, of course, is venting. So that's what we'll really be talking most about. And when we look at our PowerPoint slides here, I'll pull these guys up. We'll be looking at ear mold impressions, and then again, the effects of venting, the effects of filtering, and lastly, the effects of horns. I'll also be showing you some pieces and parts of hearing aids today too. So let's just kind of get started in this particular unit. Non-electronic acoustic modifications has nothing to do with acoustics so much and psychoacoustics, but then again it does. We'll look at the relationship therein. First of all, when we look at this, it's a lost art. Most hearing aids today are digital, which allows for an amazing amount of frequency shaping. Now look at that word, frequency shaping. It means you're literally sculpting the shape of the frequency response of the hearing aid. You know what a spectrum is, right? The horizontal axis is frequency, the vertical axis is amplitude or decibels. You know how you've got white noise as a flat spectrum. Pink noise is a sloping spectrum. Remember that? Well, that's how we describe hearing aids. What sound comes out of a hearing aid, you can make a spectrum of that sound. You can make the hearing aid give more in the treble and less in the bass, or more in bass and less in the treble, or equal amounts of frequencies across all the frequencies, okay? So it would be like a flat spectrum. So shaping the sound that comes out of the hearing aid to match the hearing loss. Because think about it, the hearing loss may go down like this, the audiogram. The person may have great hearing in the low frequencies, poorer hearing in the high frequencies. And what are you going to want to do with that? Well, you're going to want to give more amplification then in the treble and less amplification in the bass, because the person hears good in the bass but doesn't hear in the treble. So you're going to want to give an emphasis to treble amplification. That's what I mean by shaping the frequency response. So look back at our notes again. Non-electronic acoustic modifications are ways that we can shape the frequency response without ever touching any of the electronics. Just the shape of the hearing aid itself. Then you think about these things. If I pull my little sample out here, and we'll take a look at some hearing aids here, just for the sheer heck of it. Okay, let's see. Stop sharing. Okay, here we go. An example of a hearing aid. Okay, this is a behind the ear hearing aid. And on the top of the hearing aid, you can see a little tiny dot. If I make that go, look at that little dot. See that dot? That's the microphone. That's what's picking up sound. Then the hearing aid amplifies the sound, and then the sound comes out of, I'll show you something here, comes out of this little hole here, this hole. Okay, so this little tiny one on the top is the microphone. The hearing aid amplifies it, and then the sound comes out of the bigger of the two holes there. And that's called the receiver or the speaker. And then here's the ear hook. And then here's the tubing. This is the tubing, and then this is the ear mold. And the sound comes out from that ear mold. So I'll twist this guy back on again. Okay, and this kind of hearing aid is called a BTE, behind the ear hearing aid, because the mold would sit inside the ear and the hearing aid would sit behind. This here is called an ITE, in the ear hearing aid. You can see the volume wheel here, a battery door here. Open up the battery door. Okay, opening up the battery door. And again, the microphone of the hearing aid, if I take a look, see at that, well, it's kind of hard to see where the mic is on this hearing aid. Okay, would be on the faceplate of the hearing aid. Yeah, there it is. That little, see that little dot there? That's the mic. Okay, and when you turn it around, you'll see two holes. Now the white one is the speaker. Okay, and the other one, that other hole that you're seeing there is called a vent, and it's continuous with that vent. See that? So that allows an air communication to get inside the ear canal. It allows the air trapped behind the hearing aid to communicate with the air outside. It's called a vent. People use vents for various reasons. There's lots of reasons people use them. Okay. So we'll take a look at a bit of that. Oh, here's an ear mold with a large vent in it. Okay, see the tubing? And then you'll see a second hole. And that second hole is the vent. So I'll show it to you here. Okay. If I turn it around, you'll see two holes. Okay. One's for the sound to come through, and that would be this guy here. And the other one is the vent. So you can see two holes. If I hold, I know I'm trying to get it right so you can actually see that. If I turn it sideways, you'll see two pathways. See that? One's for the tubing to send the sound through, and the other one's a vent to allow air to communicate. So that's kind of what we'll be talking a bit about. Now here's one of today's hearing aid. Okay, and it's a behind the ear hearing aid too. It's called receiver in canal. And look at all the holes in this little thing that sits inside the ear. It's kind of hard to see there. You can see kind of against the green. See all the holes there? That's a vent. Those are vents. And then this tube here is really to allow it to be snug inside the ear. So I'll put this guy on here for a second. Put this hearing aid on so you can get an idea of what it might look like in the ear. Okay. So I'll struggle with this for a bit here and set that little tube in and put the hearing aid behind my ear. And yeah, you're probably thinking, this is a weird Zoom session. Okay, but no, look at that. You can hardly see the hearing aid. Okay, and that little wire that you saw hanging down, that's actually sits inside my concha bowl, and it helps hold the hearing aid in place. You'd never even know I had that hearing aid in my ear. Okay, a little bit unlike this hearing aid that I showed you here, because if I put this puppy on, okay, you see the mold, you'll see the hearing aid behind the ear. That's a larger hearing aid for a more severe loss. This is called receiver in canal hearing aid for a very small hearing loss. So a hearing aid like this is very, very common today. Receiver in canal. That means the speaker is actually inside the ear, and then lots of little holes in it for the venting. So lots of stuff we'll go over that way. Okay, share screen again. That was a little show and tell. All right. Now, read with me carefully because this involves some acoustics from earlier in the semester. Non-electronic acoustic modifications are ways of shaping the frequency response, like I'm highlighting in gray. And any hearing instrument specialist should have a good handle on these because implementing these principles is cheap. It doesn't involve any electronics of the hearing aid. What we're talking about is how the The mass and the stiffness and the resistance. Remember we covered the word impedance, reactance, opposition due to mass, opposition due to stiffness, resistance. All those three things together are called impedance. Remember that from way back in the early semester? Well, hearing aids are no exception. They all have their mass, their stiffness, their resistance, and as such they pass sound, and they're going to have effects. These things are going to affect the passage of sound through the hearing aid. Resonance of your outer ear canal or external auditory meatus. Remember we covered that it's a quarter wave resonator. It's a cylinder open at one end and closed at the other like a cup. Okay? And those things resonate with sound waves that are 4 times the length of the tube. So your ear canal is 2.5 centimeters long. It's going to resonate best with sound waves that are 10 centimeters. See the gray there? That's 1/10 of a meter. And remember, wavelength is speed of sound over frequency. Frequency is speed of sound over the wavelength. So you have to break down 10 centimeters into meters because we're saying 0.1 meter over 1. Okay, in other words, wavelength is speed of sound over x, and x is the frequency. That's what we're trying to find. So wavelength of 1 meter equals speed of sound over the frequency. So 0.1 meter over 1 is equal to 340 over x. 1 times 340 is 340, and 340 divided by 0.1 is 3,400 hertz. So the resonating frequency of your ear canal would be 3,400 hertz. But the ear canal, we always said at the first half of the semester, is flesh and bone, so that resonance is spread out a little bit. And this is spread out across from about 1,500 to 4,000 hertz, so the exact frequency is fudged a bit. The peak ear canal resonance is 2,700 hertz. Remember that in the average adult. We covered that in 120 anatomy and also in acoustics. So it's an important thing to remember, because when you take a hearing aid and when you plug an ear, okay, let's look at this picture right here. When you take a hearing aid and you plug an ear, here's an ear canal. Here's that ear canal resonance with the peak at 2,700 hertz. It starts rising around 1,500 hertz and goes out to about 4,000. You and I hear that just as natural. That's just our natural ear canal resonance. Now you're taking a hearing aid and you're plugging up that ear canal. So now you've destroyed that outer ear canal resonance. So the hearing aid may have a frequency response like this, but because you've put it in the ear canal and you have lost some of that resonance, okay, really what's coming out is this. So insertion loss due to the ear mold. So a hearing aid has to make up for that. Here's speech, spectrum of speech, just like pink noise. More energy in the lows, less in the highs. All right, so you've really got to boost up those highs anyway. And here's the sounds of speech on an audiogram. Here it is in dB/SPL, okay? Decibel sound pressure level, 0.1, 1, and 10. That just means 100 hertz, 1,000 hertz, 10,000 hertz. The energy of speech is mostly in the lows, less in the highs. When you're looking at it on an audiogram, I never know why this line is so dark all the time. It always bugs me. Let's see if I can fix that. Put it here. Can't remember. Yeah, look at this. Boom. Take it away. Now, that's better. All right. So when you're looking at this slide here versus this slide here, they're showing the same thing. This one's showing the speech spectrum in dB/SPL. This one's showing the speech spectrum in dB/HL, the audiogram. And we've all learned before that 0 dB/HL is really minimal audible pressure, that curve that you get, the softest it takes to hear all the different frequencies with one ear under a headphone. That's 0 dB/HL. So on an audiogram, of course, when the decibels increase going down, then you'll see the loudest parts of speech being the vowels and all the voiced sounds. over here in the lows and the sound softer in the highs. Okay, same thing as is shown here in DBSPL. Okay, outer ear canal resonance, the quarter wave resonator, the cup, okay? When you boil that down, wavelength equals speed of sound over frequency, all right? So wavelength is going to be, if the outer ear canal is 2.5 centimeters long, it's going to vibrate or resonate with sound waves that are 4 times the length. 4 times 2.5 is 10. 10 centimeters is 0.1 meter. 0.1 over 1 is equal to 340 over x, and you figure out x is 3,400 hertz, but the ear canal is flesh and bone, so basically that 3,400 hertz is spread out, okay, and the peak resonance is around 2,700 hertz. Well, remember now, that's going to be, and that why do we have that, of course? To help us hear the high frequency consonants. Remember, the ear is made for the throat and lips and for speech, basically. And so you can see someone's hearing loss going down here. The O's being the right ear, the X's being the left. He's got a treble hearing loss. He can hear the bass really well, but it takes more decibels to hear the treble. What's he losing? The high frequency consonants. And the outer ear canal resonance is no longer helpful enough to help, because now he's got hearing loss. So now he needs hearing aids, okay? But basically, this is the general scene. And this outer ear canal resonance is lost when you put a hearing aid in the ear. So the hearing aid really has to make up 2 things. It's got to provide amplification in the treble frequencies, and it has to make sure it recovers the lost resonance here. So it's got to kind of make up for that loss of outer ear canal resonance, plus provide gain or amplification for the hearing loss. Okay, that's the general scene. And we're looking today at 3 different acoustic modifications. Venting affects the low frequencies. Filtering or damping tends to affect the mid frequencies. And horns tend to affect the high frequencies. And that's what we're going to take a little bit of a look at today. Okay? All right. Here we go. So let's go home now. By the way, let's just talk a little bit about ear molds, okay? Because when you're taking ear mold impressions, so I'm going to show you once again an ear mold, okay? Let's look at this here, because not all hearing aids today are this. This is a stock dome. See that? This thing at the end is called a dome. And when people fit hearing aids, they take the behind the ear hearing aid, or the RIC, receiver in canal hearing aid. They'll take that hearing aid and they'll look in a box and they'll pick out the dome that's about right for the guy. And then they'll also pick out the dome that, do you want it to have 4 holes in it? Do you want it to have 3 holes in it? 2? Do you want bigger venting, less venting? Well, you know what? That's going to depend on the guy's hearing loss. Look at this. I'll show you something here. Venting really depends. I'm going to just kind of give you a head start. I'm teaching it a little differently this year. But if you're looking at venting, okay, venting, you're going to decide. I'm going to pull up this one here and look at it. If the guy has really good hearing in the low frequencies, you're going to want lots of venting. You're going to want see those holes? You're going to want lots of holes. Why? Because otherwise the guy's going to have the ear plugged up, and go ahead and plug your ear and talk. Plug an ear and talk. Hum. You hear yourself loudest in the ear that's plugged, don't you? That's called the occlusion effect. Why do you have venting? To get rid of the occlusion effect. So the better your hearing is in the low frequencies, the more you're going to get the occlusion effect when you plug an ear. So sharing screen again. If you've got good hearing in the low frequencies, you're going to want a large vent to let out the lows so you don't get that occlusion effect when you plug up the ear with a hearing aid. If your hearing is bad, worse than the lows, then the occlusion effect actually works in your favor, okay? But we'll cover more of that. It's just something I'm just giving you a bit of a head start here. Okay. Anyway, we're going to make an ear mold impression of the ear, and that is going to be for the person who is not able to wear this. Some people have a bigger hearing loss, and they can't use a stock dome end inside the ear canal. They've got to use, maybe they got to use a hearing aid like this, okay, and it's got an ear mold, and the whole mold is the shape of the guy's ear, and you are going to make this, okay? And how do you do that? Well, you do that by shaping the person's you have to make the mold yourself, so you're going to shove a sponge down in the guy's ear canal very carefully, and it's got a string on the end. And then you're going to mix your material. You're using a little ear light. This you turn on, and the light will turn on, and it will help you push this block of foam into the guy's ear canal, almost all the way up to his eardrum. And the ear canal has two bends, doesn't it? Okay, we studied that in 120 anatomy. It has two bends to it. So you're going to mix your material with a little knife like that. You may or may not, who knows, but this ear light is very important for pushing the sponge into the guy's ear canal. You're going to mix your silicone material together. You'll be shown how to do this. You'll be putting it in a syringe like this, and then you're going to be pushing and squeezing and filling up the ear canal with the material, and then you're going to let it harden for about 5 or 10 minutes. Then you'll take that out and you'll send that off to be made into an ear mold, and about a week or two later it'll come back to you in a box made. Okay? And here's ear mold impressions. You never get a second chance to make that first impression. Anyway, this is a nice, complete, accurate ear mold impression that you would be putting in a box and sending off to be made into an ear mold. Okay? This one here doesn't have sufficient canal length. This one here, it's the undersized canal as well. It's always better to have the two bends in it. You can see one bend here and a second bend here. Okay? So it's showing you the two bends. Your ear canal is like a dog leg. Okay? You want the full concha, the full helix, the tragus. All right? You want the whole darn thing. This one's an unfilled helix. It's not complete. It's always better to give too much, because the manufacturers can always shave off what they don't need, but always overdo an ear mold impression. These are styles of ear molds. Now remember, these are more for severe hearing losses, people who have to wear regular behind the ear hearing aids. Okay, and I'm just showing you the pieces and parts here. Why not? If I open this up, there's the battery door. Close the battery door. Here's the on-off switch. Okay, these little wires on the bottom would be so you can clip something on, like a boot, that you can communicate with an FM system. Don't worry about that now. This is a volume control on the hearing aid. Okay, so this is meant to be a high power, fairly high power hearing aid for someone with quite a severe loss. RIC hearing aids, today's hearing aids, don't give as much power, and notice they don't even have a volume control. Okay, it's got a mic and stuff like that, but no volume control. That's because the hearing aids today use something called compression. They give more amplification to soft sounds, less amplification to loud sounds, so they automatically change volume. Automatic volume control, or automatic gain control, AGC. It's a word called compression, and you'll be learning all about that next year in a course 240. By the way, the course number is 240, and the hearing aid's called, or the course is called Compression and Digital Features. So you'll learn way more about that then. These are much more popular than these, because most people have mild to moderate sensory neural loss. Mild to moderate sensory neural loss, much like the audiogram that I showed you in this picture here. Okay, when you're looking at this picture here. Mild to moderate. Okay, down to about a 50% hearing loss in the highs. Mild to moderate. Mild in the lows, moderate in the highs. This would be typical presbycusis. And typical presbycusis can easily get away with a hearing aid like the RIC hearing aid that I'm showing you. Receiver in canal. Very, very common. Common. Okay, so looking at the ear molds that we just did, just want to, here's some styles of ear molds. This one's called a full shell. And you can see it's covering the whole thing. Okay, that's a lot like the ear mold that I showed you earlier. So if I stop sharing here, that's a lot like this ear mold. Full shell. Okay, it's all made out of silicone, rubber, you can bend it. It's all, okay. Share screen. This one here is not completely full shell. This one here is called a skeleton, a lucite skeleton ear mold. I'm wondering if I've got me one of those puppies. Yeah, here we go. I can show you a skeleton ear mold myself. This middle one, okay? I'll show you a picture, show you one here. That's a lucite skeleton ear mold. See how, and again, it's meant, I'm going to say this ear mold is really meant for someone with a real whopper of a hearing loss, like a severe to profound hearing loss, because you don't want any sound leaking out. That silicone's going to stick to the walls of your ear canal like glue. It's not letting any sound leak out from the hearing aid at all, because the sound leaks out, you're going to get feedback. Okay, and what is feedback? That's when the mic is too close to the speaker. So what's coming out of the speaker, okay, is coming into the mic. So I've moved too close to the speaker. So not only is my voice coming into the mic, but also sound from the speaker is coming into the mic. Then you get that vicious circle, and you get the hearing aid that whistles. Today's digital hearing aids have automatic feedback reduction, but feedback is a big issue with high power hearing aids. You don't want to cause the feedback, so you want a full shell ear mold. Loose, it's not made out of lucite either, it's made out of silicone rubber. You can bend it. Okay, see this ear mold here, you can't bend. It's made out of, okay, it's made out of plexiglass. Okay, this is called a lucite skeleton. This is called a silicone full shell. Silicone full shell lucite skeleton. This is meant for someone with less of a hearing loss. Notice this one's got a vent in it. Okay, so this one might be meant sort of like for a moderately severe loss. All right, and then the most common, of course, is today's RIC hearing aids with just the stock dome. And that's what they call it. It's not even an ear mold, it's a stock dome. And this little, remember, you had that little wire is simply anchored, just lays inside your concha bowl like that. And it helps to keep this stock dome nicely in your ear canal. That's why you always see that little thing hanging down there. Anyway, okay, pieces and parts of hearing aids. Why not? All right. So this style here is not so, is sometimes used with RIC hearing aids because sometimes the dome isn't quite right for somebody. Maybe the person's got a kind of a different kind of ear canal and kind of wants his or her own custom mold made. The most common of the two molds that I'm trying to show you are the silicone full shell on the left and the lucite skeleton in the middle. Very common. All right. Yeah, okay, the next one's coming. Oh, I know what it's doing. It's just non-occluding, da-da-da-da-da. Don't worry about these. Next. Ha! Guess what? Someone, when you're taking an ear mold impression, it's going to actually look like this. The material may be green or whatever, okay? This was taken in Toronto, Ontario, Canada, an ear mold impression. Students at George Brown College in Toronto. That's an HIS program there, okay? And they were practicing taking ear mold impressions on each other. And one of the students had, what do you call it, a thing in her ear? What, I don't know, one of these, you guys know what they are better than I do. Let's see, a barbell piercing of the crus of the ear, okay? Today in class, a student got an ear mold impression stuck on a barbell piercing of the crus of the ear, Okay, so there was something, it took 15 minutes of very careful cutting to free the impression. So they actually really had to cut the mold open. You could see it was a nice ear mold impression, the whole concha bowl there. But right here, they had to split it all apart in order to get it out of the student's ear. I thought it was kind of funny. Anyway, so let's look at what happens now. We'll take a peek at our notes and see where we are there, okay? I'll stop sharing here. I just want to get to the notes. Okay, the notes. Here we are, okay. All right, so that first part of the page is largely talking about the ear canal as a quarter wave resonator and showing you that, the emphasis of the high frequency consonants and the outer ear canal resonance naturally helping you hear the highs, all of that stuff. The middle of the page, we're looking at lucite skeleton, okay, softer materials for kids, that's silicone, reducing feedback due to a tighter fit. That would be, you should write in here full shell, right where my arrow is. And lucite skeleton is also used on BTE hearing aids for a lesser hearing loss. But today the most common, of course, is RICS, okay? Receiver in canals. Venting, dampening, and horns. So horns and filters. Now, of these three, the one we're covering the most is venting, okay? Venting is the big one, because it reduces the occlusion effect. Damping or filtering isn't used quite as much today as it used to be, because today's hearing aids are digital and we can really get around the need for filters digitally. Same with horns. They're not used as much today either. I'll be describing them and you should kind of know what they are, but of the three, venting, filters, and horns, venting is the big one and it's used all over everywhere, okay? Horns and filters were relied upon mainly in yesterday's analog hearing aids. They're not used as much in today's digital hearing aids. But remember, there's a bit of a tension between vents, horns, and feedback, okay? Venting, the first acoustic modification, and horns, the third one. We're not talking filters, just venting and horns. Horns increase the highs, but highs might leak out of the vent. And then you're going to get feedback. Okay, let's talk. The 4 words we hate to hear. We need to talk. So if you have a high power BTE hearing aid, okay, and let's say on this hearing aid, I'll take off this mold and I'll put on this mold. Okay, so now you have the hearing aid. A high power hearing aid with a vent, because you got that, you can see the vent, the hole right there where my pinky is, okay? So if this hearing aid is high power and it's pushing a lot of sound through here and it's going through the tube and it's going through this top tunnel into your ear canal, and here, say my fingernail is the eardrum, sound's going to bounce off that eardrum and leak out of the vent, which is the bottom tunnel, and it's going to get picked up by the mic. Here's the mic. A little hole. Okay? So that's what feedback is, right? Sound from the speaker gets picked up by the mic. Same with a high power hearing aid. Sound from the hearing aid is bouncing out and getting picked up by the mic. It's amplified, sent down, bounces off the eardrum, leaks out the vent, gets picked up by the mic. Same thing as me talking in a mic going too close to the speaker. Same vicious cycle. That's what I mean by the tension. There's a little bit of a between feedback that can happen and the size of the vent. You may want to reduce the size of the vent, but then you're going to be increasing the occlusion effect. You'll lessen the chance of feedback, but you'll get more occlusion effect. So that's what I mean by there's an art to this. It's not just all a science. There's a mixture, and you, the clinician, have to balance things at times. I guess that's what I'm trying to say here. Share screen. So that's what I mean by this tension here. Anyway, let's look at venting in itself. Short, wide hole in ear mold done to reduce low frequency amplification. Mark that down. Reduces the lows. How come? Because you're creating more acoustic mass. Why? Because you're letting sound. You've got the air space trapped behind the ear mold, but you're letting it communicate with the air outside. So you've increased the acoustic mass of air by means of a vent. And what's going to happen with the lows? They're going to follow that increased mass. Just like Hansel and Gretel followed the crumbs of bread to get their way out of the forest. Okay? Lows resonate with mass. So you've increased the acoustic mass of air by means of having a vent, and the lows are going to therefore follow that, and they're going to go out. So that is how vents reduce the occlusion effect. And that's the main thing to tie in with vents, occlusion effect. It's done when you're plugging up an ear and you hear your own voice louder when your own ear is plugged. And that's the occlusion effect, and that's the reason for venting, because with a hearing aid, you're plugging up the ear, so you're going to create the occlusion effect. So you need to have a vent to increase the acoustic mass so that the lows can escape. Because what is the occlusion effect? Let's make sure we have this down. I'll give it to you two ways. The occlusion effect, the simple definition, and the professional definition. So write this down. The simple definition, your voice is louder when your ear is plugged. Okay, that's the simple one. Your voice is louder when your ear is plugged. The more complicated definition is, jot it down, okay? Low frequency, that's the first one. Bone conducted sound. What the heck does that mean? Well, air conduction comes from your mouth and the sound reaches the ears. Bone conduction means this the loudness of your voice, your larynx, okay, vibrating the bone of your skull, okay, and going to your inner ears. So you hear yourself through air conduction and bone conduction. You hear others only by air conduction. That's why your voice on a recording sounds different to you. When you're hearing your own voice on a recording, you're going, "Ugh, is that me?" Everybody says, "Yep." You're the only one that doesn't think so, because that's because you're hearing yourself through air and bone, whereas you hear others only through air conduction. Anyway, back to occlusion effect. Low frequency, bone conducted sounds resonate the mass of your skull. So there's three things. Low frequency, bone conducted sound resonates the mass of your skull, which in turn resonates the cartilaginous portion of your ear canal. Okay? And 5, plugging your ear prevents that resonance from escaping. So there's 5 things to it. Low frequency, bone conducted sounds resonate the mass of your skull, which in turn resonates the cartilaginous portion of your ear canal. Plugging your ear prevents that added resonance from escaping. That's the professional definition of the occlusion effect. And it's a common thing. What's the main complaint of hearing aids? Number 1, background noise. Number 2, occlusion effect. Number 3, feedback. Okay? Background noise, occlusion effect, feedback. And we mess around with occlusion effect and feedback by means of non-electronic acoustic modifications. And feedback is also dealt with digitally, with digital anti-feedback, digital feedback reduction. So we don't rely on non-acoustic modifications as much to get rid of feedback. But feedback used to be dealt with mostly by filters, the second acoustic modification. But let's stick to venting for now. Let's just mainly talk about venting here. Venting, a short, wide hole in the ear mold done to reduce low-frequency amplification, creates more acoustic mass, thus allows the lows to leak out. Larger vents allow more lows to escape out. They reduce the lows more. So the bigger the vent, the more the lows go out. Venting reduces occlusion effect, which is especially important for people who have good low frequency hearing and high frequency hearing loss. Then there's something called selective vent. Well, let me just show you this so you can see this. I think it's always important for you to be able to see these things. Selective vent. Okay, if you were ordering an ear mold and it came back like this, you had an ear mold. Now look at that big hole for the vent. Okay, there it is. You can just see it right. I'll point with my pen. Right, hang on. There. Okay, right there. That's the hole. So I mean, there you go. I'm sticking my pen right into that hole. So you can see the size of that, okay? So what often came with the molds is a little tree like this. And notice when you're looking at this carefully, maybe hold it against my shirt, you can kind of see it better. As you're moving from left to right, the holes are getting bigger and bigger. Actually, they're getting, this one's totally filled. This one's a large hole. Okay, this one's a little bit smaller, a little bit smaller, a little bit smaller. The size of the round thing is the same, but the hole inside is different. Okay, so that's what's called a selective vent. So what someone does when you get an ear mold, this will come with it, and you can plug up that vent hole with the selective vent. So you can choose the size of the vent hole that you want based on the client's observations of the occlusion effect, and also based on how much feedback you're getting, adjusting for that tension. So you can adjust the size of the vent yourself, and it's largely a trial and error thing. There's no magic formula to it. You as a clinician would work with the client on this. Selective vent for VTEs or ITEs. One large vent with a series of progressively smaller plugs from 0.8 to 4 millimeters allows you to customize venting for a client without drilling and ruining the ear mold. So let's see if we've got a picture of that as well in your notes, or in your PowerPoints, I should say. So let's move on down here. And here's a picture of selective vent. Okay, SAV. So here you're looking at the tubing going into the ear mold, and then you're looking at the vent, and you're looking at the plug. And that's what I showed you on that tree. And you can choose the size of hole that you want in that plug from 0.8 millimeters all the way to wide open 4 millimeters, which would be this size right here. Okay? So essentially, we're talking 3 different modifications here. Okay? Venting on the left, filtering or damping on the middle, and horns on the right. See how the horn gets wider, wider, wider? Now, when you have a horn, you're increasing the highs. Filters were used to reduce feedback, okay? And vents were used to reduce the occlusion effect. So the 3 particular, again, the modifications. We haven't talked much about damping or horns at all, but again, I'm just showing you context here. Seen here, okay? And again, on the left, venting, filters, horns. Venting, filters, horns, affecting the lows versus the mids versus the highs, okay? Selective vent. Now, how do people make vents in hearing aids? Well, the top one is the best, okay? If you're having an ear mold, I'll stop sharing. If you're actually having an ear mold, see how that's a parallel vent? All right, that's a good vent. Those are the best ones. If I share screen and show you a lousier one, okay, a diagonal vent. Those aren't very good. They were put in, though, when there literally wasn't enough real estate in your ear canal to handle the 2 parallel tunnels. So parallel vents are the best, but in some people with small ear canals, they made a diagonal vent, and that's not as good, because what happens is not only lows escape, but also highs. So you're really reducing. It's not a very good way to do it. External vent is just a parallel, and then see where it ends right at the ear mold itself? There's no ear mold material to surround the bottom. It's better than nothing, okay? The top one is the best. If you can get away with that, that's by far the best way to go. So here's a picture showing you what venting does. Okay, dBSPL along the vertical axis, frequency along the horizontal, and what's the effect of venting? Well, a closed ear mold with no vent, there's no reduction of the lows. A 1 millimeter vent, a little bit of reduction. 2 millimeter, more of a reduction. 3, more reduction. And and then here's the open ear canal. All right, showing you again the influence of vent diameter on the occlusion effect. Here it's showing to you in terms of gain or in terms of dB. Same idea though. Okay, low frequency damping, or you're getting rid of the lows as a function of the diameter of the vent. The smaller the vent, the less the reduction in the lows. The bigger the vent, the bigger the diameter, the more the reduction of the lows. Okay, and that's what's most important to realize about vents. Let's read it here. Parallel versus diagonal vents. Parallel is better. Diagonal vents tend to let out up to 10 dB of highs as well as the lows. Pressure vent, there's a definition for you. Pressure vents are just small vents. Pressure vents are 1 millimeter in diameter. So look at the dashed line, 1 millimeter. It lets out barely any lows. Pressure vents are used mainly for physical comfort. They just allow the air to communicate on both sides of the mold, so that when you pull out the hearing aid, you're not sucking out the eardrum. Okay? It's just a pressure vent is not really meant to affect the occlusion effect, to get rid of the occlusion effect. It's mostly just a physical comfort thing. The bigger the hearing loss, usually the less the vent. Also, the better the hearing is in the lows, okay, the better the hearing in the lows, the bigger the vent. Venting is mainly a low frequency reduction. It's a reduction of the lows to overcome the occlusion effect. Very small hole is a pressure vent meant to equalize air pressure. It's a comfort issue only, not really meant to modify the acoustics. Note on PowerPoint slides where vents are seen on BTEs and ITEs. Let's see if I got a picture of that. Where are they seen? Okay. Just again, take a peek here. The BTE, just a picture. This is how we'll wind up today's discussion. Here's a BTE. There's the microphone. Now in here where I'm circling, that's the speaker, or what we call the receiver. Volume control. OTM switch means off telephone mic. M means on. Okay, in English, off and on both start with an O, so we don't know which is which, so they're always called OTM. Off telephone mic. You'll learn more about the telecoil later on. Battery compartment. Here's the ear mold tubing, the ear hook, and the ear mold. This would be a lucite skeleton, as you can see by the hole there. Okay, and again, turning the hearing aid sideways a bit, the ear hook, the mic, volume control, special features controls, OTM switch, battery compartment. Looking toward the right, you can see the guts, volume control, and the telecoil is an interesting thing. A telecoil in a hearing aid is meant to be used with the telephone. And it's a magnet wrapped around with copper coils, and inside your telephone is one of those too. And it shuts off the mic, and it allows you to hold the hearing aid right up to the telephone, and you're hearing by electromagnetic conduction through the telecoil in the hearing aid and the telecoil in your telephone. So the mic is now off. It gets rid of any chance of feedback. You can hold the phone right by the ear, because another thing with feedback is if you held your hands close, because you're guiding any leaking sound to get picked up by the mic. So anyway, that's the BTE, the basic parts. And again, the mic, the hearing aid, the receiver or speaker, the ear hook, the tubing, the ear mold, here's its vent, location of filters that we'll talk about next week. Okay, filters are usually in the ear hook of the hearing aid, in the ear hook. And just I'll give you a picture of what here. I'll show you a filter here. See that little red thing in the ear hook? That's a filter. That little red thing inside of here. That's a filter. Filters are actually tiny little screens. So if I share screen, I'll show you. Speaking of screens, okay? Hang on. Here, screens. That's a filter. Filters were meant to dampen the peaks. Here's a frequency response of a fictitious hearing aid. Just a fictitious hearing aid, okay? And you can see that it's got lots of whoop, 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 okay? Lots of peaks. And those peaks are just resonances of the internal guts of the hearing aid, because they all have mass and stiffness as well. And filters were just seen as a way to get rid of those peaks, because those peaks cause feedback. Feedback is caused by high frequency sounds leaking out. Because why do highs leak out so much? Why is it the highs, not the lows? Because highs bounce. High frequency sound waves are short. And short sound waves bounce. Long sound waves bend. Remember that? Highs bounce, lows bend. So we'll talk more about that next week and about why highs cause feedback and filters and all of that. And then we'll talk more next week as well about horns. And so when you get over to good old horns, whoops, I got to make this thing advance here. So filters get rid of the peaks. So the more filtering you have, the less peaks you have. Okay? And horns, look on the left. When you make something wider, you increase the highs. And that largely can be demonstrated if I grab a piece of paper here, and I'll just demonstrate for you horn quickly. Okay? Just in case. Take this guy here. Wrap it like so into a horn. Okay? If I talk into the wide end of the horn, my sound is muffled. But if I talk into the small end of the horn, my S's and F's and CH's are all emphasized. My high frequencies are emphasized. My high frequencies are damped here, are blocked. And if you want to find out how an elderly person hears with high frequency hearing loss, make a horn and talk into it, because that's how they hear. They don't hear the consonants very well. So hearing aids have to take this frown and they've got to turn it upside down, if you know what I mean. Okay, so basically, I'll stop here. We'll finish this session next week, Tuesday at 11:30 Central Time, and that will be your last Zoom session of 110 acoustics. So we'll have spent 2 weeks on non-electronic acoustic modifications. Today we mainly went through venting. Next week we'll kind of recap and review a little bit of what we covered today, and then we'll go on to filtering and horns, and I'll be describing tubing a little bit more to you, and then that will be that. And we'll finish with more of a discussion of RIC, hearing aids, and all these things. So it's been a slice. It's been a spectral slice. We'll see you next week. All right, I will stop recording here and sign out.